All right. My name is Curtis Bowman. I am the chair of the UALink Consortium. And let me start off by thanking everyone for joining in today. We really appreciate the audience. I also want to say thank you to our panel members, a great group of folks who have looked at scale up across the years and really understand what scale up needs to do in the environments around AI. And so with that, let me kind of say that, the reason we came together is because we had a white paper published through TASK Consultancy, and Jimmy Pike, who is the author, is with us, as well as members of the board and members of UALink Consortium. So let me have them introduce themselves. Chris, let's start with.
Thank you, Curtis. So my name is Chris Peterson. I'm a VP and technologist here at Astera Labs. So I lead the team in the CTO office, and I also represent Astera Labs on the UALink board of directors.
Thank you, Chris. And Josh, you're next in line.
Hello, everybody. My name is Josh Collier. I'm a senior principal engineer at Intel. My focus is around GPU accelerator networks and a strong interest in UAL, obviously.
Thanks, Josh. Ishwar.
Good morning, everyone. My name is Ishwar. I work as a machine learning SoC architect at Meta, specifically on the MTIA line of silicon, and very interested in scale-up technologies in general. Thank you.
Priyank.
Thanks, everyone. I'm Priyank Shukla. I'm Senior Director of Product Management at Synopsys. I manage the scale-up and scale-out IP portfolio at Synopsys, and I'm also Secretary of UALink Consortium. Great to be in the webinar today.
Well, welcome, Priyank, and the other UALink folks. And then Jimmy, why don't you introduce yourself?
Yeah, thanks, Curtis. I'm Jimmy Pike. I am the founder and a senior fellow at TASK Consultancy. I retired. I have 49 years in the industry, so I guess I can't stop. So I retired from Dell 5 years ago and started this consultant firm. And while I am the author of the paper, I would really call myself the co-author of the collection of a lot of extraordinary people who put input into this paper.
All right. Well, thanks, everyone. And, the audience continues to grow, and this is recorded. So if you know of somebody who would be interested, please feel free to give them the link so they can listen to it afterwards. But let's just jump right in. So, as we start with the paper itself, and I'll reach out to Priyank for this first one. What are your key takeaways from the white paper?
Promise, this is the one time I'll summarize this white paper without using the phrase "it depends." So my biggest takeaway is this. AI system performance has crossed a threshold where this is no longer a compute problem or compute bound. It's a bandwidth bound problem. And historically, the industry has been forced into an uncomfortable choice, either proprietary, vertically integrated fabric that deliver great performance, but you lock in, or Ethernet derived solution that are open but were never designed for accelerator memory fabric or traffic. What this white paper makes very clear is that UALink is fundamentally removing that trade-off. A few technical points that really stood out for me was first, UALink is a purpose-built stack, not a retrofit. The protocol, transaction, data link layer, and physical layer are co-designed. They're co-designed for accelerator to accelerator memory semantic. It supports native reads, writes, atomics as the first class citizen, not something which are tunneled over a general networking abstraction. The design choices show up directly in both latency and efficiency. The performance claims are really backed by concrete numbers. This paper details and articulates them really well and put those numbers in context. We are talking about roughly, if I remember correctly, 93% effective bandwidth efficiency, sub-microsecond round-trip latency over short copper link, and optimized 64 to 256 byte transaction, and a large unified memory fabric space. And this is a really huge space, which we have put number there in the white paper. And finally, the economics matter is also very important. Now in 2026, the economics matter as much as the architecture. And UALink deliberately writes the IEEE 802.3 PAM4 Ethernet physical layer ecosystem. This means the industry shares cable, connector, retimer, and avoids duplicating physical layer qualification with every generation. So this white paper highlights that we have a protocol that's purpose built for AI fabric, delivers top commodity performance at high volume manufacturing.
Excellent. Well put. Anybody else on the panel want to jump in on that question? If not, I'll remind the audience that if you also have questions that you'd like to pose, there is a place to input your questions, and we'll get to them at the end. We'll try and save a little time at the end to answer your questions. So Jimmy, let me come to you next as kind of the author of the paper. What kind of surprised you the most as you researched UALink and scale-up ecosystems in general?
Well, it's very interesting to look at the way we've looked at this over years of bandwidth, latency, efficiency, congestion management, and bounded variances. Those are all lumped into a lot of discussions, and I think we focus a lot on bandwidth. We focus a lot sometimes on latency. Then we get into congestion management, and then the idea of determinists or bounded variances. The problem is that this is a finely honed system. If you can't mess up in one, because if you do, if you have any one of these slip, you'll get a congestion. A congestion can result into a tail latency event. And once you get a tail latency event, you start getting your synchronization stall. When stalls like that happen, you can have 1,000 GPUs that are out there doing a reduce all, and that turns into real clock time that costs real money. So as Pri says, the fabric has to be engineered as a whole, not assembled from independent parts. And the things that we've done in the past that kind of were the assembly of these parts, that's sort of past. And so now, if you look at what's been happening over the last couple of years, people have taken some of the things that we actually described in the UALink paper and have engineered them into interconnects that didn't traditionally have those. But the whole idea is the whole fabric must hold together. You have to, if you inherit layers and you inherit links and you inherit stalls, that shows up in the end of the system, and you'll really be surprised how it really turns out when you're doing stuff like large learning models.
So Jimmy, on that, or maybe others on the panel, as you're looking at a kind of holistic view, what are the key things that you need to keep in mind when you're specifically looking at a scale-up fabric? What are those key parameters?
So maybe Curtis, I can chime in here as well.
Yeah.
So I think as we look at the requirements for a modern scale-up fabric, there are a few that have already been mentioned, and I'll add a few more. So certainly, of course, these days, we are bandwidth challenged, as Priyank was alluding to. And so trying to get to the maximum bandwidth density, in other words, the amount of bandwidth that you can get out of a particular piece of silicon, the area required for that is important, right? So, focusing on building on top of the Ethernet physical layer to give us that is a key, one of the key requirements. Latency has also been mentioned, but I think that the key point that Jimmy was alluding to, and I will reinforce here, is that it's critical that the latency end to end, as you're executing these models, needs to be deterministic, right? I think it's not just enough to say, okay, I have low cut-through latency as I'm sending a handful of packets. The systems are loaded, right? So we care about these tail latencies, and we care that it's deterministic. I think the other key requirement here is that radix is important, right? So And I would actually quantify this as what I would call sufficient radix. You could, of course, always build a fabric that can scale to thousands or tens of thousands, hundreds of thousands of nodes. But really, the focus for scale up has always been on hundreds to maybe 1,000 or low thousands, basically. And so UALink's been very focused on that specific solution space, and quite intentionally, because you can always go higher, but that comes at a trade-off. So making sure that we're building something that is also efficient in terms of the bandwidth utilization, it becomes a key characteristic for that.
Excellent. Thanks, Chris. Any other input from the panel? If not, let's move on. Josh, let me toss this one towards you. How do the findings influence the way we think about accelerator interconnect requirements?
Thank you, Curtis. Yes, so the paper has quite a bit of findings here that tie very closely to these workloads. So let's kind of, let me touch on them a little bit here. One of the key findings is the open nature of the specification. What this does for us is it provides accelerator vendors, and there are many of them in the world. It provides us an ecosystem and opportunity to build these systems that we wouldn't have otherwise, right? A lot of this would have to be done behind closed doors, would not, create all sorts of other problems, interoperability, and doesn't bring together many companies and innovative ideas together in one place. Often we're better together than we are alone. So that's key. And that's a key requirement for anybody building an accelerator these days. So having that openness is an important finding. The other things are, this technology it's aligned with memory semantics. The paper talks about how the memory semantics is there, and there's many attributes to them, but this aligns very closely with our accelerator architectures. So as a requirement, it was a key foundational attribute of the specification. The other pieces I'll say are, while there may be not direct requirement or influencing these findings, they are key to the overall product development and the efficiency that we have, including the high efficiency of the link protocol itself is extremely efficient, and that lends to improvements in power efficiency and shoreline. The scaling that we've already talked about, that you can scale these systems to 1024 accelerators, that's key for many of these workloads, and that's a requirement in many cases. Low latency, maybe we haven't touched upon it as much, but low latency is a key finding for this architecture, that it contributes to that, and that's key for getting the efficiency in the workloads that we need. And other areas like power and silicon efficiency are also very important for us. So all these tie into what we'll call requirements to build a very competitive and interesting product in today's era.
Excellent. Hey, Josh, you touched on low latencies, and I think Jimmy talked about tail latencies being an impacting factor. For people who are maybe newer into this area, how do you differentiate a latency versus a tail latency, and why are they important to differentiate?
Sure, that's a great question. So when we talk about low latency, we're kind of talking about your typical memory access time. How long does it take for one, accelerator to write the memory of another accelerator over this network? And we're looking for sub-microsecond access latencies. That's directly shows up in every collective transaction that you may have on this network. When we talk about tail latencies, we're usually talking about a probabilistic case where a packet could get lost or corrupted, or there's something that happens on the link and a packet needs to be retransmitted. One of the things UALink does very well is that it brought forth a link layer reliability protocol, which is very low latency. So if anything happens on the link, if we get an uncorrectable FEC error or a CRC error, we're able to retransmit that packet very quickly and recover it so that that error does not manifest into a large workload impact that's seen by the workload. if you have 1,000 accelerators all trying to come together in some sort of barrier, and one of them ends up taking, a few extra microseconds or even milliseconds, that's all wasted efficiency. So tail latencies are more, they tend to come out of error situations that you're recovering from, or congestion cases, rare congestion cases. And when we talk about low latency, we're really just talking about kind of average memory time.
Thanks. All right. Ishwar, maybe we'll get you in the mix here with this one, but certainly others in the panel jump in as well. But what advantages does the white paper suggest UALink provides over alternative interconnect approaches?
So I'm from Meta, and as Meta, we evaluate a bunch of different interconnect technologies for both scale up and scale out. And UALink is of interest to us for several different reasons, I think some of which have been mentioned by other panelists before me, the efficiency, the low latency, semantics. But the thing that I focus a lot on over here is how the primitives exposed by UALink are very generic. They read, write atomic semantics, and they map very cleanly to a number of different accelerator architectures, as well as up the software stack to different communication libraries, and further up the stack to MPI synchronization primitives. It's a very easy, clean fit from all the way from PyTorch down to the accelerator architecture, and then down to the UALink semantics. In addition to the clean mapping of the UALink semantics up and down the software stack, it provides a very, I'm going to double down on the efficiency factor a bit more, not just the link efficiency, the low latency. I think Josh touched about it right now. The tail latency is of particular importance, and the clean architecture provides a very bounded tail latency for UALink. And then finally, because the architecture is clean and elegant, the actual implementation of the architecture in silicon also tends to be very, very efficient in terms of the area and power consumption. So all of them, when you combine the software interfaces to the efficiency in terms of the KPIs for performance, and then the implementation efficiency in terms of area and power, I think there are some very good reasons to be super excited about UALink compared to some of the other interconnect technologies out there.
Excellent, thank you. All right, so Chris, let me pick on you a little bit. Would you characterize or how would you characterize UALink in terms of kind of the product cycle where we're at?
Sure. So I think I would view this as two parts, basically. So the phase that we're in right now, the 1.0 spec was released a little over a year ago at this point, and the 2.0 spec came out roughly a month ago. So the phase that we're in now is there's a lot of design and implementation work happening. There's a whole ecosystem of design IP, verification IP, basically all of the silicon components that you need to be able to integrate this successfully on both the accelerator side as well as in the context of a switch. In addition to that, there's a lot of work happening in the ecosystem around the test and measurement equipment, so that when the silicon is back, you have some way to characterize it, you have some way to validate it. And there's a bunch of work happening around the software side of things as well, right? So the management spec, for example, was fairly recently released, and there's a whole code base that comes with that, and that's getting integrated into the management software stacks. And I would actually expect us to be at the point where you could imagine that there's likely to be some demos of some of this coming up this year. And I think the key takeaway for me is that we're at the point not only where things are being implemented, but actually if you compare it to the objective of UALink in general in terms of providing this performant low latency memory semantic fabric, really it's something that from a parity perspective is working towards being parity with something as advanced as NVLink in 2027. So I think we're very much headed in that direction. I think the second part, though, that's also worth mentioning here is not only is there work happening on implementing UALink and driving towards production products, but the progress hasn't stopped, right? So we always need to be thinking ahead about what comes next. What does the next generation product require? How do we continue to make improvements? So as with the UALink 2.0 spec that was just recently released and the continued effort basically in the consortium, that effort continues, right? So this isn't a one generation or even two generation effort. The goal is to make this multiple generations and continue to drive forward progress, even as we're working towards productizing the first generation.
Well stated. In fact, I'll jump on it as the chair of UALink. There's always opportunities to jump into UALink and help us improve where we're going with our interface. And so if you're a member of UALink, please join the work groups. If you're not a member, please join. And with that advertisement aside, back to the paper. Priyank, let me come back to you. What role do interoperability and open standards play in enabling a scalable, efficient, and composable AI infrastructure?
It's a very relevant and great question, Curtis. And when we talk about interoperability and open standards, I see three very practical roles, not just philosophical ones. And this is where UALink Consortium has added great value. First, the open standards create a level playing field for innovation. Any chiplet or silicon vendor can implement an interface without negotiating licensing agreement. This interconnect technology is an open standard. The same protocol works across different types of connectors, cables, switch port deployment, management layers, and they cleanly work with SAI, Redfish into existing data center workflow. This means the best technical idea are not blocked by business friction. The best innovation gets a real chance to scale, reach mass deployment, and ultimately win on merit. So that's number one, topmost. Second, I see interoperability is what prevents the lock-in tax. And this is where the open standards come in. UALink, as we have been talking about, it's an open body which is governed by 115 plus companies. And our consortium spans across hyperscalers, silicon vendors, system companies, and IP providers. So this group just does not publish a specification. It enforces a protocol compliance, as we are going to come up with a compliance workshop, multi-vendor interoperability testing, and performance characterization. So without that enforcement, and so-called open spec quickly turns into collection of incompatible implementers. And this is where UALink is shining. And this is where this open standard enable composable ecosystem. And finally, open standard inherent ecosystem velocity. What I mean by this is because UALink rides on Ethernet PHY roadmap from transition from 112 to 224 and now to 448 gig, every PHY generation lifts UALink performance automatically. A proprietary fabric has to fund that reinvention if there is a different PHY physical layer involved, and the whole new generation of physical layer has to be reinvented for that proprietary protocol. But in open ecosystem like UALink Consortium, the whole industry can move together faster. And that's how the strongest solution emerge and win.
Great, thank you. I think the next question, Chris, maybe I'll come to you just because you and I, we've worked across a number of different industry initiatives in different companies and et cetera. And one of the things that we see when we're doing the work is getting it implemented in silicon and then in the system and on into environments where it goes into data centers. Where do you see UALink in terms of the product cycle that's ongoing? You kind of mentioned one of your answers that we're getting close to maybe demos, but where do you see it kind of getting into tests in labs and then maybe later into data centers?
Sure. So I think at this point, Curtis, we're very much on track towards likely seeing silicon towards the end of this year, which means it'll be up and running in labs within weeks after that. And you can expect at the cadence that things move in the AI space at this point, that it'll be in data centers shortly thereafter, right? I mean, these days, it's a question of weeks and not months before some of this AI silicon goes from sufficiently brought up to let's run this at rack scale in a data center. So I would say certainly towards the end of this year, or getting into early 27 is a realistic time frame for that. And starting from a spec and to getting that into silicon, it's actually quite a rapid pace, right? So if the UALink 1.0 spec came out last year, that's basically from spec completion into full blown silicon up and running in less than 2 years is quite impressive. Many of the other specs that I've worked on, it often takes quite a bit longer than that. But of course, in this AI era, that's the pace that's required.
Definitely agree. We've got a lot of great member companies, and the speed at which they have pushed UALink into the specification and then into the market has been impressive. And that's where it takes a village, and then the advantage of having a consortium. So kind of ask question for the group about the paper and what we see, and then we'll get into the Q&A from the audience. We've got a couple already, but if there's more, please enter them now. But to the panel, kind of what do you see on the horizon around UALink or scale-up networks, and what do you see coming next out of the consortium? Maybe Jimmy, I see you got a hand up. We'll let you start.
Yeah, Curtis, I tell you, this is one of the things that I think this is a revolutionary space, and let me tell you why. I think we've talked a lot about UALink as a fabric and what fabrics do, and high-speed fabrics and the open ecosystem, et cetera. But I think what UALink is going to deliver in addition to this is this memory model, this hardware-driven memory protocol that is built into the transport. The idea of being able to, whatever your GPU or your accelerator is, see a common memory model that allows you to exchange with your partners, or whether they be the same company or the heterogeneous ecosystem we're headed for, to have that in a specification where people can write to that specification regardless of what their ISA is on either end of the specification, and be able to effectively communicate. I think that's a revolutionary change it can bring. And we're looking at this era that we're approaching where heterogeneity is going to be all over the place. And unless we have something like this specification and this protocol that everybody can conform to, not that there's an ISA that has to do that, but that you can make any ISA map to that, I think that is a huge, huge step forward in making a real heterogeneous ecosystem possible. And I think years in the future, we're going to look back and we're going to see, oh, UALink was a great fabric, and it brought us this ability to have this heterogeneous memory map ecosystem among our accelerators.
Absolutely agree. One of the things that maybe Josh, you could talk about is, 2.0 spec just came out that Chris mentioned it about a month ago. One of the big pieces we added there was INC, or in-network collectives. Why is that an important piece in a scale-up environment?
Thank you, Curtis. Sure. We're really excited about all these new changes in the new 2.0 specification. Between the many security enhancements that are there, as well as one of the major features, which is the in-network collectives, the collective offload feature. UAL has worked hard. The consortium has worked hard to define two major modes for collective offload, and both have really significant benefits to many of these workloads. So especially in the training workload, AI training where all reduce is used heavily, there's a lot of immediate benefit for this collective offload in UALink switches. And we feel like that's going to be an immediate benefit for everybody that's able to deploy that. Additionally, today there are people who are doing inference workloads and they're trying to scale tensor parallelism to reduce token latencies. And when doing so, as you increase reduce those latencies, you increase your tensor parallelism, and you there as well, you benefit from having switch coordinated all reduced capabilities. And that's not where we're going to stop, right? We're continuing to look at what's going on as you said, what's on the horizon for beyond 2.0. 3.0, we're going to reevaluate additional features that are we're constantly looking for how to make these workloads more efficient and higher performing.
Excellent. Ishwar, any other comments around, kind of what you're looking for in the future, what you're looking for a scale-up environment?
So as Josh mentioned, firstly, we are very excited about the in-network collectives and the promise that in-network collectives has in accelerating different workloads and reduce collective latencies, especially for the most common cases of tensor parallelism, as well as perhaps expert parallelism. Going forward, looking forward to what is going to be required from scale-up networks. I think we're seeing the radix of the scale-up networks scaling to a higher and higher radix as opposed to staying stagnant or going lower. And what I think we're going to be looking forward to in UALink as we go to 3.0 and beyond is going faster, going wider, adding more robustness, and making it a more general purpose fabric for perhaps a multi-rack solution at some point.
Excellent. And panel, what do we think about optics as we go forward, especially as the speeds increase? Optics versus copper, where do we see that line being drawn?
Yeah, so Curtis, maybe I can chime in on this one. So before I talk about optics, though, I do want to build on one kind of key point that Ishwar was just alluding to, and that's robustness. We haven't talked too much about reliability in these fabrics yet, but I think Josh also alluded to the importance of the tail latency and the fact that often that's driven by error conditions or corner cases. So I think focusing on reliability, especially as we go to higher radix, higher scale, is increasingly important. These rack architectures are incredibly complex, right? There's many tens of thousands of differential pairs in these racks at this point. And so errors are not a corner case anymore, but kind of a fact of life. And so we need to be able to deal with that and actually design it into the layers of the stack from the beginning. And I'll point to one specific example here. In the UALink 2.0 spec, one of the features that we added is a capability called link resilience. And I like to call it out because it's done at a sufficiently low level of the stack that it allows us to deal with a lane failure without having to actually stop traffic, right? So yes, of course, there's a performance implication here, but the point is that you don't have to stop all of your traffic, completely restart it, and replay everything, right? So it's a low enough level that you can deal with this event in hardware automatically. And I think that's the type of optimization that as a UALink consortium, we tend to focus on. So the reason I bring it up in this context is that certainly in the context going forward as we go to higher radix as well as to higher speeds, we're going to have to look at optics. There's really no way around it. Just the aggregate bandwidth density required, the number of connections coming in and out of the rack is going to require optics at some point. So it's definitely going to be a big focus for the consortium and UALink in general going forward. So I think it's reasonable to expect that optics will be a key component of that. And then, of course, how do we make sure we're building that in such a way that it is also sufficiently robust and reliable? And it will be certainly part of the discussion as we investigate how to address this going forward.
Well stated. Other input there?
I would like to chime in there, Curtis, as well. People have been talking about deployment of optics, maybe using co-packaged optics or near-packaged optics for a long time. At this time, we definitely see light at the end of the tunnel for optics, so to speak. Co-packaged optics has always had this challenge. The performance of the optics, how it behaves with respect to operating condition, with the temperature change. Now the industry has seen significant proof point that convinces the cluster implementer that co-packaged optics is a viable option. And now we are seeing cluster grow so big that the optical links are the only power efficient and reliable solution. So there are a bunch of designs that we are starting to see which are enabling UALink over optics for next generation deployment. Synopsys, being an IP vendor, gets this hindsight view of what's happening in the ecosystem, and there's a lot of resonance of UALink riding over optics. So we are really excited of making this technology take shape in data centers.
Thanks, Priyank. All right. Any last inputs from the panel before I go to some questions that have come in online?
Curtis, one earlier we discussed a bit about open standards and their benefit. And I think one key area that probably didn't get a whole lot of attention on this is that the open standards, when it comes to security, are absolutely critical, because if you're a customer buying any of these products, how are you to trust that somebody has done a good job in securing your data without the transparency that an open standard gives you? And UALink has gone through the trouble of standardizing the security that we provide to tenants that use this hardware. And I think that is a key differentiator compared to many other solutions that is really important and drives the open standards requirement.
Great point. Thanks for bringing that up. All right, so a couple questions that came in online. The first one, I think we've talked a little bit about it, but we'll close on it. How is the tail latency reduced or bounded in UALink versus other interconnect technologies like PCIe?
So Curtis, I can add more to that as well. I would say that UALink and PCIe have similar strategies for dealing with the tail latency. Both have a link layer reliability protocol that they employ. Both try to drive switches that are low latency. So they're very similar in that nature. UALink is actually trying to drive much higher bandwidth through the same shoreline. PCIe unfortunately has lagged in that with regard, what's starting to ship today is 64 gigabit SerDes, and UALink has our specification for 1.0, which came out over a year ago, has been driven based on the 224 gig SerDes standard. So that's part of it is making sure this happens with the right technology at the right time.
Excellent. Any other folks want to jump in there? Otherwise, I'll move to question number 2, which is, go ahead.
Sorry, Curtis, I'll add one other quick comment there. In particular, comparing to PCIe, so often in these types of fabrics, generating writes is important. And as efficient and effective as PCIe is in many applications, one of the downsides is that there is no response to a write. And that's important from a software perspective, because as Josh was alluding to earlier, the entire stack is involved in driving tail latencies. And if you don't have a response back to a write, software doesn't know that that write has arrived correctly. So it has to use other mechanisms to confirm that the data is actually where it is supposed to be. So in UALink, every request has a response. So you will know immediately as soon as the request has gone through the entire loop that you've gotten a response, and therefore software can easily move forward and not have to worry about that. So that will also improve your tail latencies because you're not sitting there waiting for a response to come back or to send another command to confirm it.
Okay, thank you. Good point. So the next question, we'll probably have to do some clarification here too, but the question is, how close the UALink speeds will be aligned to Ethernet speeds? With the example they put in here of Ethernet's already at 448 gig, UALink is still at the 200 or 224 gig. When do we expect these to catch up? So I think we need to just kind of help on that one. And maybe I'll start. The UALink and IEEE are very highly aligned on the PHY layer. So that 224 gig PHY that the industry talks about at 200 gig, that's the version that's just really being ratified now by IEEE. Now the IEEE has started work on the 448 gig solution, and we're working closely with the IEEE members on that and understanding it. But it's not something they even have a draft spec for at this point. When you're looking at trying to do 400 gig per link or per lane rather, and so I think that we're keeping up very closely with them. But it's just a matter of where they're at in the specification and whether or not it can be deployed. Now, one thing you can do, of course, and UALink is the same way, is you can aggregate your lanes to make a link that would be 200, 400, 800 gig. And that way you can take advantage of higher bandwidth on a given link by just aggregating those lanes. I don't know if anybody else on the panel wants to jump in to talk about
Curtis, let me
yeah.
chime in a little bit too. So, one of the ways that an accelerator gets bandwidth, scale up bandwidth, is it doesn't implement a single port. It usually implements multiple parallel ports, multi-railed. And actually, it turns out when you're really this efficient on the wire for your transactions, it's actually difficult to increase the port bandwidth. So that's why in our UALink specification, we talk about an 800 gig station and a 400 gig that can be bifurcated into two 400 gig ports. It can obviously run as a single 800 gig port or 4 200 gig ports. And it's not clear from a technology perspective that we would want to necessarily increase the bandwidth of a port. Ethernet today, certainly there are 1.6T ports, possibly even higher speed, depending upon how many lanes you want to aggregate together. But what ends up happening is when you're dealing with these small transactions, where you're dealing with a transaction per clock cycle, it gets very difficult to manage inside accelerators when you're dealing with many transactions in a given single clock cycle. And so, again, we're striving to get aggregate bandwidth across a multitude of ports. That other benefit that lends itself to is that you can get flatter networks, because if you go deploy large bandwidth ports, you need a switch that has a comparable radix with ports of large bandwidth. If you want to get a larger network with a higher scale of thousands of accelerators, you're actually better off usually with thinner ports, like lower bandwidth ports, but many more of them in parallel. So I think the speed issue here is not so much what bandwidth port we are targeting to. I think maybe it's hard to understand the full intent of this question. is the question more around our ability to drive a lane speed and what a lane is? Because when we pivot to optics, the concept of lanes may change, right? Optics on a single fiber, you can have many different wavelengths of light, and you can modulate those wavelengths at different speeds. Optics will easily get you to really high bandwidth, but that can actually be a downfall at the same time, because managing that bandwidth at a switch can be very difficult if you're trying to build, 2 terabit port times 1,000 ports. That's a difficult switch to build, right? So, but I agree with you, Curtis. We are aligned with IEEE. If there's, technology they're ready to deploy, UALink can easily adopt to it.
Yeah, but great point on, it's really a system view that you have to take when you're deploying something of this size. So thank you for that. That brings us to the end of the questions. I want to thank the panel for all your help, and I would give Jimmy, as the author of the white paper, did you have any last message that you wanted to send to this group?
No, I think this has been well covered. I appreciate a lot of the responses I've gotten personally over the web, and just keep them coming.
All right. Well, again, thank you, everyone. Thank you to the audience. And if you have further questions, we've got a website that you see here at the bottom of the page. Feel free to jump out there and send questions that way as well. I hope everybody has a great day.
Thank you.
Thank you.